Hello, welcome to the last lecture on artificial neural networks of the computational intelligence course at TU Delft. In this lecture, I'm going to talk about associative memory networks and self-organizing maps. These are two biologically inspired models that follow the unsupervised learning paradigm. We will discuss what this means in a second, but unsupervised learning differs from supervised learning because we are not provided any labels. We can only rely on our input to learn the hidden features, but we're not given any feedback. Then I'll introduce Hopfield networks and bidirectional associative networks, which are two classes of associative memory models. And finally, I'll talk about self-organizing maps, which try also to capture the data to find these hidden features while preserving the topology of the input. So the material of this lecture is going to be the book by Michael Negnevitsky, Artificial Intelligence, and I want you to read sections 6.6 to 6.8. And then to go a bit more deeper, we have here the book by Raul Rojas, Neural Networks, and we're going to cover chapter 12, chapter 13, and chapter 15. And again, this goes a bit deeper into the topic. So if you're interested, it's a good read. So yeah, I encourage you to have a look. Okay, so unsupervised learning differs from supervised learning, as I just mentioned, because we are not provided any labels. What that means is that if you recall from the first lecture, in supervised learning, we had an input X that we pass through our function, our neural network, which we can denote by f of x, and the neural network contained a series of weights, a set of weights, and then this function will output a prediction, y hat, and we will compare that prediction with the true label. So what we did is we optimized the full neural network, optimized by calculating the gradient of the error of that prediction and backpropagating those gradients through the network to optimize and to update our weights. So we were learning a mapping from input to output. Now we don't have an output, we don't have labels, so we can only find the structure and try to capture the hidden patterns in the data. So it's more like a feature learning. And the most common applications of unsupervised learning are clustering. So in clustering, we can have a data cloud, something like this. So we can have one data cloud here, and another here. So this could be so this is the entire data set, and it could have this structure. And then in unsupervised learning, we want to learn this structure. So one way to do so will be maybe to model these two clusters by using a normal distribution. And so we could try to fit a normal distribution to this cluster maybe, and another normal distribution to this other cluster, so that the mean mu1 and sigma1 of this normal distribution capture the density in this area, the density of data points in this area, while the mean of this other normal distribution captures the mean or the behavior of the density at this other area, in this other cluster. So, it's a way of trying to represent your data with fewer features. Then we also use this for dimensionality reduction. So a very common technique is called PCA, Principal Component Analysis. that tries to find a lower dimensional representation of your data. Is used very often for visualization, but you can also use it like if you have too many features, maybe you want to reduce them before training a model, because that might allow you to find a better representation, find a better transfer function. So in practice, as a summary, what we do is we try to learn useful representations of our data. We have no labels, but we can still try to learn how these inputs are structured. Like in this particular case, we had two different clusters that we could model with a normal distribution. So this is the new task that unsupervised learning is trying to solve. Okay, so let's talk about bidirectional associative memory models. And these are models that try to emulate the human ability to associate new experiences with patterns or concepts that are stored in our memory. So if you think about when you watch a movie and then you see the face of a familiar actor, then that face might remind you of another movie, which might trigger your memories about the people that you were with when you watched this other movie, right? So this is precisely what we want to model with this bidirectional associative memory models. If you think about the way a computer accesses information, they use location addressable memory. So that means that in order to access information in the computer, you need the physical location of that information on the disk. On the other hand, humans use content addressable memory, and that means that in order to access our memories, we only care about the content of the input. So that input will trigger a memory, and then we will be able to retrieve it. Okay, so this is precisely what we want to model. And say, for instance, that we have a set of inputs, x1, x2, x3, x4, and then we feed them into our network, like so. Then we multiply them by our matrix of weights, W. We pass them to the activation function, and we obtain y1, y2, y3. So this process is pretty much the same as in feed-forward neural networks, as in multi-layer perceptrons. But now what we do is we take our new output and we feed it into the network from the opposite side. So we feed now y1, y2, y3 from the opposite side. And then we multiply again by W and obtain our new inputs, x1 prime, x2 prime, x3 prime, x4 prime, which will be different from these inputs here. So, okay. So this, by the way, is W transpose, so that we can keep the dimensions of our output. And this is W, it's the same matrix. Okay, so as you can see, what we do is we first feed our inputs into the network, and then compute the outputs, and then use the same outputs to obtain new inputs. And we repeat this process again and again until our this sort of dynamical system converges to an equilibrium. And an equilibrium occurs when the inputs and the outputs do not change anymore after processing them with the neural network. So let me just write that a bit more formally. So we have that y, the first step, y0, can be computed as the sine of W transpose times x0. And the sine function is pretty much like the step function, but instead of 0 for negative values, it's -1 for negative values. And then it's 1 for positive values. So this is the sign function. So this is the activation functions that we use in bidirectional associative memory models. Then if we want to compute x again, so in this case x at time step 1, we just need to feed our outputs again into the network. So we feed y0 now. So this will be the sign function of w times y0. And then we check if the input is the same as the output, as the previous input. And if that's the case, then we have found an equilibrium. If not, we continue iterating. So an equilibrium, or fixed point, occurs when y equal to the sign of w transpose x and x is equal to the sign of w times y. The equilibrium occurs when this x here is equal to this x here and this y here is equal to this y here. And when if we continue iterating back and forth between inputs and outputs, then these values here do not change. So that's the equilibrium. Now the question is, how do we find W? How do we find W, the correct matrix of weights, right? Okay, so one way to process or to learn the matrix of weights is by applying Hebbian learning. And Hebbian learning was introduced by Donald Hebb in 1949. And it's just a learning algorithm in which the motto is that neurons that fire together wire together. And what that means is that if two neurons are simultaneously active, then we should encourage that interaction between the neurons. Whereas if two neurons are uncorrelated or their activations are uncorrelated, then we should discourage their interaction. Okay, so if I write that mathematically, we have that the new value of W prime, is equal to the previous value of W plus correlation of the input, X, and the output, Y transpose. And this is an outer product. So this will be basically measuring the correlation between the elements in the input and the corresponding elements in the output, how strongly correlated they are. And because normally X and Y are bipolar vectors, that means that they can only take values of -1 or 1. So these are essentially like binary vectors, but instead of 0, we have -1. This means that if two elements are uncorrelated, the correlation will be -1, which will mean that that particular element in the network will be decreased, or the particular weight will be decreased. And if they are correlated, then this will output a 1. So we'll increase the weight of that particular element, which is good, right? This is what we wanted to do. We wanted neurons that fire together to wire together. So we're discouraging uncorrelated elements and encouraging correlated interactions. Okay. So let's try to store one memory in our model, because essentially this is what we want to have. We want to have a model that where we can store memories and then we can retrieve them when we get similar inputs. So our first memory is going to be x1, y1, this input-output pair. And the way we're going to store this is by applying Hebbian learning. So our matrix of weights will be W will be equal to W prime will be equal to the previous value of W plus x1 times y1 transposed. And initially we set this to be equal to a matrix of zeros. So essentially we get that W prime is x1 times y1 transpose. So the correlation matrix of these two vectors. Okay, so let's just check now that if we feed x1, we will get y1. So let's just check that it doesn't change. So that this is an equilibrium point. So we have that y1 should be equal to the sine function. For this to be an equilibrium point, we have that W transposed times x1 should be equal to to y1. Okay, so we have that the sine of Wt times x1 is also the sine function of y1 times x1 transpose, because the transpose of this is y1 times x1 transpose times x1. And now we see that this is actually the 2 norm of x1. And because these are bipolar vectors, if this was x1, and then I took the 2 norm of this bipolar vector, then you could see that essentially this second norm is equal to 3, which is the number of elements in my vector. So more generally, if we have n elements, then the 2 norm of a bipolar vector is n, the number of elements. So then we have that this is a positive value, so it won't change the sign, and we are left with this here, which means that the sine of this is going to be equal to y1, because y1 can only be either minus 1 or 1. So y1 can only be minus 1 or 1. And this is positive. And this guy is positive. Cool. Then let's just check that if I feed y1, I will get back x1. So x1 should be equal to the sine function of W transpose times, now it's not transpose anymore because we want to keep the dimensions. So now it shouldn't be transposed. And now we have W times y1, and this is equal to the sine of, now we have again this guy here, because there is no transpose, so it's x1 times y1 transpose times y1, and this is again the 2 norm of y1, which is, if y has m elements, then it's equal to m, and also it's positive, so it won't change the sign. So we can write that the sign of this term here is x1. So this proves that now x1, y1 is an equilibrium point, because after processing it through with a network, it doesn't change. The equilibrium remains the same, or the point remains the same. Okay, let's just now try to store a new value, because, we want to have multiple memories stored in our model that we can retrieve depending on the input that we're getting. So if we store a new memory, x2, y2, then that would mean that we just need to take our Hebbian learning update. So we'll have that W, in this case, prime maybe, is equal to our previous W W prime, plus now x2 times y2 transpose. And I'm going to call this x1 times y1 transpose, I'm going to call it w1, because it's the matrix of the correlation matrix of the first input pair. And now I'm going to call this guy w2. Okay, so now what if I still want to add a new memory? So now I'm going to add x3, y3. So again, I'll just do the same. So I have that w prime 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 is equal to w prime prime plus x3 times y3 transposed, and this is just equal to w1 plus w2 plus w3. So we add up together the correlation matrices. And okay, so now let's just see, because now we have stored a lot of vectors here. So now we might need to actually retrieve this, and then we want to check if we can find an equilibrium point. So if we feed x3, are we going to get back y3 or not? Okay, so we can essentially check that. So we have y3 is equal to the sine function of, now we have that is w1 transpose times x3 plus w2 transpose times x3 plus w3 transpose times x3, right? And this is also equal to the sine function of, we know from this expression here, from this one here, that this is y1 x1 transpose times x3, and this is y2 times x2 transpose times x3, and this is y3 times x3 transpose times x3. Okay, so, and essentially we want to get this, the sign of this, right? And that means, let me just write this here, that we need the absolute value of y1 x1 transpose times x3 plus y2 times x2 transpose times x3. We need this absolute value to be smaller than y3 times n. And I write n because this is the 2 norm, again, so this is n. Okay, so that essentially means that we need y3 to be greater than this expression here, y1 x1 transpose times x3 plus y2 x2 transpose times x3, the absolute value divided by n. And this is known as the perturbation term. This is known as the perturbation term or crosstalk. So the reason we call it perturbation term or crosstalk is because it can actually interfere in safely retrieving the equilibrium points, in safely retrieving our memories. So if this crosstalk term is larger than our output of the equilibrium, then we won't be able to retrieve that memory. So more generally, we can write the crosstalk as Ct is equal to the summation of I different from J M, and then we have yi times xi times xj xi transposed, and then we divide by n, the number of elements in the input. And this should be lower than the absolute value of yj. And we know that because this is a bipolar vector, that the absolute value of yj will be essentially a vector of ones. So each of the elements in this summation, in this vector summation, should be lower than 1 for the network to be able to retrieve the memories that were saved. Okay, because these are bipolar vectors, it's likely that they are orthogonal to each other. So x1 could be this one, for instance, and x2 could be this one. So if they're both orthogonal, that means that if I multiply x1, if I take the inner product of x1 and x2, I will get just the value of 0. So these elements here are likely to be 0, which is good, right? And even if they are not completely orthogonal, if they're just slightly closer, if the angle is not 90 degrees but it's slightly less, then this value will be the inner product of this term, x2 prime and x1 will be still very small, and therefore we should be still able to retrieve the memories. But with high probability, these two vectors will be orthogonal, which is good, right? Okay. So let's say I want to memorize handwritten digits, and for instance, I could have x1, y1, which could be encoding the digit 4. And then I could have x2, y2, which could be encoding, say, 3. Now, if I memorize these two, then my matrix of weights will be W1, the correlation matrix of x1, y1, plus W2, correlation matrix of x2 and y2. So this is essentially x1 times y1 transpose plus x2 times y2 transpose. So now I memorized, by using Hebbian learning, I memorized these two digits. And now say, for instance, that I get a new input z, which encodes a value for this new handwritten digit, which is also 4, but it looks a bit different from the previous 4 that we had. So hopefully, if I fit this into my network, I should be able to recall this previous memory using this matrix of weights. So let's check that is actually happening. So now y will be equal to the sine function of my matrix of weights w transposed times z. And this can be also written as the sine function of y1 x1 transpose times z, because the transpose of w1 is y1 times x1 transpose times z, and then we have plus y2 x2 transpose times z, the transpose of w2, and then this is equal to this should be equal to y1, and this will hold if and only if y1 x1 transpose times z, right, is the absolute value of this is larger than y2 times x2 transpose times z, because we want this term here to dominate and we want the sign of this value here. Okay, cool. So that means that if we have two vectors, x1 and x2, this will basically hold if C is closer to x1 than to x2, which is fair, right? Because if C is encoding this 4, C should be closer to x1 than to x2. So therefore, C could be a vector like this, and the inner product of these two vectors will be larger than the inner product of these two, and therefore this inequality here will hold. But what if we now want to store a new vector, a new digit? Say we want to store x3, y3, which is, I don't know, encoding the 100th digit 5, this particular 5 here. Now the question is whether y1 times x1 transpose times c will be larger than y2 times x2 transpose times c plus y3 times x3 transpose times z. And if these two guys are two dimensions, like in this particular plot, then this is less likely now. So in general, we want to check whether what's the maximum capacity of a network. How many models, how many inputs and outputs pairs I can store in my model so as to be able to still recall the memories that I stored. And so that's called the capacity. Maximum number of patterns that I can store. While being able to recall them, right? So it's important that I can recall them. Okay, so that's related to my crosstalk term, CT, and that was equal to 1 over n of the summation of I different from j to m, the number of elements in I, of yi times xi transpose times xj. Okay, and one can show by making a few assumptions that if we call k the number of patterns, k is the number of memories or patterns that we want to store, then the size of my input, the size of x, which we are going to call m, should be at least approximately equal to 0.18 times k, the number of memories that I want to store. And this thing is obtained by making a few assumptions about the way these inputs are selected. If they're selected at random, then we can calculate the probability distribution of these weights and therefore find the area under the curve. And, like we can say, I want this probability of the crosstalk term, I want this with a higher probability of 99%, I want this value to be larger than 1. The absolute value of this, I want with a high probability of a probability of higher than 99%, I want this to be larger than 1. And therefore, I can obtain an estimate of how big my inputs need to be. Because it makes sense, right? Like the bigger this input vector is, the larger the number of elements in X is, the higher the capacity of this network will be, right? Because the more inputs I will be able to store. All right, so let's just move on. So let's talk about the energy function. The energy function is just trying to give values to each of the states that I visit while I'm trying to converge to the equilibrium. So the energy should get smaller and smaller as I move closer and closer to the equilibrium. And it will reach its minimum right at the equilibrium point, right at the fixed point. Okay, so let's say, for instance, that I start from an initial value x0 and I multiply that with the weights of my network, W transpose, and then I pass this through the activation function and I get y0. So then I can compute the value of the energy here, x0, y0, and this value should be larger than the energy after one step, according to what I just said. So the energy after one step will be at a step. So if I pass this through my network from the opposite side, then I'll multiply by W and I'll calculate the activations and I'll get a new value for my inputs, x1. And then the energy at this new point, x1, y0, should be smaller than the energy at the initial state. So that's basically the idea. And the energy is defined as minus 1/2. This is just a constant that is multiplying x transpose times W times Y. And now I'm going to call WY, I'm going to call it my excitation, and I'm going to denote it by E. So this is the excitation of my input neurons. And similarly, I could also call this the excitation of my output neurons, and I could call it G. So this is also equivalent. This will be XT times W times Y, and I could write this as minus 1/2 of G times Y. I could write this as minus 1/2 of XT times E. Okay, so now I want to check that basically if I plot this, if I plot X, this is my vector X, and this is my vector E, then what I mean by decreasing the energy is essentially that this E will move closer and closer to X, will move closer, E prime, closer and closer to X until it reaches the equilibrium point. And as you move closer, the inner product is larger, and therefore this inner product is larger, and therefore the energy is lower because of this negative sign here. Okay, so that means that eventually when I reach the equilibrium, my two vectors E and X will be on top of each other, and therefore I will have reached a minimum for this function here. Good, right? Because when my excitation matches my input, it means that I have found an equilibrium point and I'm not going to move from there. And that equilibrium point has minimum energy. And this is precisely what we wanted. Okay, that's good. So let's just now check that the increment in energy is negative, or maybe that E at the first point, that E at the initial state is larger than E at the first step. So E at the initial state x0, y0 should be larger than E at x1, y0. So this should be positive. Okay, so this is basically minus 1/2 of x0 transpose times E0 minus plus 1/2 of x1 transpose times E0. the same excitation because I have the same output y. And then because this is an inner product, this guy is an inner product, I can write this as minus 1/2 of the summation over j from j equals to 1 to n of x, or I think I called this m before, so from j equal to 1 to m of xj0 times ej0. So I multiply every element in x by every element in e. And then I subtract the other term. So this is also the summation over j from j equal to 1 to m of x1j times e0j. And now let's just say that x1 and x0 differ in just one element. They differ from each other in just one element. So let's just say that the element j in x1 is different from the element j at x0. And if the energy is smaller at x1 than at x0, when we change just one element, then it will also hold that the energy is smaller when we change more than one element. So let's just take that the energy is smaller for a single element when we change a single element. So then we have that all the elements, or these elements in this summation, will cancel out because they will be the same except for xj. So we'll have that this will be xj minus, so 1/2 minus 1/2 of xj at 0 minus xj at 1 times the excitation vector, or the element in that excitation vector. Okay, so let's check the two options that we have. So we could have xj0 being equal to 1, and that would mean that xj1 is equal to minus 1, because E is what E has excited x1 to be different. So E has changed the value of x1, and therefore if x0 and x1 just differ in this particular element j, then that means that E0j is also minus 1. So it has changed, Ej has helped x to change the sign in at that particular element. And then if that's the case, then we can check that minus 1/2 of 1 minus plus 1 times minus 1, and this is positive. So E, or the increment of E, is positive. So from the initial state to the first step, or first state, the energy has decreased because this value is positive. And then we have that xj0, the other option will be that this guy is minus 1, and therefore xj1 will be 1, and ej, because it has to have the same value of as xj1, ej0 needs to be also 1. And then we can check that minus 1/2 of minus 1 times 1, that is also positive. So E is also positive, which means that this thing here holds. The energy at the initial state is larger than the energy after just one iteration. Okay, good. Let's just talk about Hopfield networks. These are just a particular case of bidirectional associative memory networks. And the reason they are a particular case is because now our input X and our output Y are the same. So here I can have 3 neurons, 1, 2, 3, and these are still my neurons 1, 2, 3 after I update them using the weights of my network. So another way of representing Hopfield networks is by using this other diagram in which I have 1, 2, 3, so the 3 neurons. And the reason we can represent it like this is because now we're not moving back and forth between input and output anymore. We're just updating the values of our weights in every iteration. Sorry, the value of our neurons in every iteration based on the interactions with the other 2 neurons. Okay, so these memory networks are also called auto-associative networks, and the reason is that one because input and output are the same. So we're not moving back and forth between Y and X. We're just updating the values of X. So that's why they're called auto-associative memory networks. Then another particular thing about these networks is that the values are not updated synchronously. We just sample in every iteration one of the neurons, and we update its value based on the other 2 neurons. So maybe, for instance, I sample this neuron here, and we just update the value of this neuron based on the value of this neuron 1 and the value of this neuron 2. There are 2 conditions for stability. One is that the matrix of weights needs to have a 0 diagonal, and this is already shown in the diagrams. We see that the neuron does not connect to itself, so a neuron does not affect its future values. So there is no connection between a neuron and itself at the next time step. So this is the first condition for stability. So the 0 diagonal, no connections between the neurons and themselves. And then the other condition is symmetry. The matrix of weights needs to be symmetric. That means that the values here should be equal to the values or the elements here. And this was already met in bidirectional associative memory networks because we were using the correlation matrix as our weight matrix, and the correlation matrix, as you might know, is always symmetric. So that we already have. But now let's just check why these 2 conditions are important. So let's just start with the matrix with non-zero diagonal. So it could be -1, 0, 0, then 0, 0, 0, -1, 0, and 0, 0, -1. This could be 1, for instance, 1 weight matrix with non-zero diagonal. And let's just say we have now here an input X, that is X is equal to 1, 1, 1. Now, if we multiply this input, if we do like before, and let's just think that this is now, we update these things synchronously, just for this example. Now we'll have that the new value of X, X1, is going to be equal to the sine of W times X. Now, because my matrix is now symmetric, is now a square, I don't need to take the transpose. So I can just multiply W times X, and the value of X prime will be -1, -1, -1. And if I do this again, X2 is going to be equal to sine of W at X1 times X1, and that will be equal to 1, 1, 1. So my model is just going to cycle and be flipping between these two states, -1, -1, -1, and 1, 1, 1. So this is why this particular neuron or this particular configuration is not stable. And the other condition was that the matrix of weights need to be symmetric. So let's try with a non-symmetric matrix of weights. So now we have 0 diagonal, but the matrix is not symmetric. So this is W. This was also W. And now let's just update these things synchronously. Sorry, asynchronously. So for instance, let's just say we have x1 is equal to 1, 1. And now we have that if we want to update the value of x2, we have that this is the sign of w1, 2 times x1. And w1, 2 is -1, so x2, so -1 times 1, that will be -1, so x2 become -1. So now x2 is equal to 1 minus 1. And then if we update the value of 1 now, sine of w to 1 times x2, x2 is minus, this is positive, so I'll get also a -1, so x3 is equal to -1 minus 1. And then I can update the value of x2 again, and that will be -1 times -1, so -1 times -1, that will be essentially 1. So I will have x4 will be -1, 1. And again, I will be cycling through this 4 steps forever, so it's unstable again. So let's have a look at how we update the weights in a Hopfield network. And the learning algorithm differs a little bit from the one we used in bidirectional associative memory networks. And the reason is because we don't want the elements in the diagonal of the weight matrix to be different from 0. We don't want our neurons to be connected to themselves. So, okay. So the learning algorithm looks like this. So we have wij, a particular element in our matrix of weights. wij prime is equal to its previous value, wij, plus the correlation between a neuron and another neuron. So xi, the value of a neuron at a particular time step, and the value of another neuron at the same time step. So the reason it looks like this is because we want to encourage neurons that fire simultaneously and discourage the interaction between neurons that are not correlated. And this applies to I, j from 1 to n, except when I is equal to j. So I needs to be different from j. And this is the diagonal. So this is because we don't want the elements in the diagonal to be updated. So in matrix form, we can write this as w prime is equal to w, the previous value, plus x times x transposed, and then minus the identity matrix, right? And the reason we have the identity matrix here is to ensure that the diagonal remains 0. Okay, cool. So let me just calculate the energy at a particular point. The energy, say, at 0. So let's first memorize one input. So we can memorize x1, memorize x1. And the way we're going to do so is by updating our matrix of weights. So W1 is going to be equal to the initial value of the weights, which is 0, plus x1 times x1 transpose minus the identity matrix. And let's just compute the energy at a particular point, say at the generic point x. So the energy at x is going to be equal to minus 1/2 of x transpose times W1, my matrix of weights, times x, right? Because now this in BAMs was y, but now input and output are the same, so now we have x. And this is equal to minus 1/2 of x transpose times x1 times x1 transpose times x, right? Minus x transpose times x, because W1 is this. And now we know that x transpose times x is equal to n, because this is a bipolar matrix, so the 2 norm is equal to the number of elements in that matrix. So then we can write the energy as minus 1/2 of the 2 norm of x transpose times x1. So the 2 norm of this matrix vector multiplication, so this vector multiplication, plus n/2, so this here. Okay, and then we see that this energy function has a minimum at x equal to x1. And so that proves that x1 is an equilibrium fixed point with minimum energy. Good. So let's look at the demo of how Hopfield networks work in practice. So I have here a demo. So I can add an input pattern, and then I can memorize that input pattern, and then so then I can try to recover that input pattern from a corrupted input. So let me add an input pattern like this one here. So this looks like a T, and let me learn that input. Okay, now I learned that input. Let's just try to add a new input pattern. Like this one here. And I learned that input. And then I try to maybe learn a new input pattern. Maybe this one here. Something like this. Something like this. So this is an E. Capital E. And then I also learned that input pattern. Good. Then let's just try to send a corrupted input to check whether it converges to the actual. So let's just send something like this. This looks like a T, but it's not exactly a T. And let's just hope that it will converge to the T I just memorized at the beginning. So let's just run 10 iterations to see if it converges. So now you see that some of the elements have changed and are white and not blue anymore. Let's just try to run another 10 iterations, and another 10 iterations, and another 10 iterations. And now we see that another element has changed and has been replaced. And then if I run the whole thing until I find the convergence, until I reach an equilibrium, I will eventually find my memorized input pattern. So this is how Hopfield networks work, right? Like we memorize a set of input patterns, and then we try to send corrupted inputs and try to find whether this Hopfield network converges to the right input pattern, to the memorized input pattern that we learned. All right, so let me finally introduce self-organizing maps. These are also neural networks, and they are trained via unsupervised learning as well. So here we could have a set of neurons like this, 1, 2, 3 neurons, and each of them will have a set of weights, W1, W2, so these are vectors, W3. And then we could have an input x, which could be something like x1, x2, xn. Normally the number of input elements is larger than the number of neurons. And so we have a whole data set of inputs, and the task consists of finding or assigning the inputs that are similar to a particular neuron. So neurons will try to accommodate or try to find samples that are similar in our cluster, and we basically try to get assigned to those. And the way we do so is by applying this competitive learning algorithm. So initially, the weights of all these vectors, W1, W2, and W3, which by the way have the same dimension as x, so they are n times 1, because x has n elements. Then all these vectors are initially initialized at random. So we just give random values to all the elements in these weights. And then we sample an input from our dataset. So say our dataset is this, and then we sample an input. This could be x1. And then what we do is we calculate the distance from this input to each of the weight vectors. So if our weight vectors are like this, maybe W1 is this one, and then we have W2, and then maybe W3 is something like this, and then our input, the sample that we got, maybe somewhere here. So we calculate the distance from this vector to these other vectors. And this could be the Euclidean distance. And the one that is the closest to this vector, x, is the one that is selected. So that's why it's competitive learning. We select only one, the closest one, and we update the weights of that vector. So the way we update the weights is like so. So W prime, the new weights, are essentially W, the previous value, plus the learning rate times x minus W. So what this means is that, for instance, if this vector was selected because it was the closest to x, then if x is this vector and W is this other vector, W1, then this update rule will bring W closer to x. W prime is now closer, W1 prime is now closer to x. Okay, so for instance, we could have a data set which would contain movies, and these movies will be somehow like encoded in a certain way. So we could have a set of properties for these movies that will characterize them. And essentially, maybe there are two variables that define how these movies are. So x1 and x2. And we could have, I don't know, like maybe 3 types of movies. We could have action movies, we could have sci-fi movies, which we could represent with a square. So action movies are represented by a circle, sci-fi movies with a square, and then we have drama movies, which we represent with, say, I don't know, an X. Okay, so then we can basically plot this. So this is how it looks like, maybe. So action movies are here. Then we have sci-fi movies, which are here. And then we have drama movies, somewhere here. Now, what we will see when we apply this competitive learning algorithm is that our weights, say for instance that by just random initialization, W happens to be closer to this group of, to this element here, to this input here, so then it gets selected. So this is W1. And then it will be moving towards this here, and then because it's already closer to this guy, also closer to this guy, also closest to this guy, then perhaps X or W2 that is here and W3 that is here, then it will get assigned to this guys more often, or it will get assigned always to these guys because the distance to them is smaller, and it will basically try to accommodate all of them. So it will be gradually moving towards the center of the different clusters. So this particular cluster here. So maybe in the end, W1 end up somewhere here. And the same will happen to W2 and W3. They will be moving towards a particular cluster, which is, they are assigned to it by just random initialization. So they will be moving towards that particular cluster and basically position themselves at the center. So this could be the final position for W3, and this could be the final position for W2. Okay, but if we run this algorithm again, it might be the case that now W1 gets assigned to different classes. So maybe W1 is now assigned to this other cluster, and W2 is assigned instead to this cluster here. So this just depends on the random initialization, right? Like how far each of the weights are initially from all these clusters. So in practice, this is not very useful, right? Because we want to sort of preserve the topology of this in the input data. Maybe the fact that, you know, action movies and sci-fi movies are closer to each other than action movies and drama movies has some relevance, right? Like it's something important that we care about, and we still want to have or preserve that property in our new representation, right? So after assigning all these neurons to a cluster, we still want neurons that are close to each other. We want to represent somehow related clusters, right? And this is precisely what we do when we train self-organizing maps. We want clusters that are close to each other to encode similar information. So we provide the neurons with a certain structure. So for instance, we could have like a structure like grid. So we could have like 9 neurons, and we could structure them in this way, maybe. Or we could have maybe another structure that will look more like an hexagon. And the idea is essentially that this structure should be preserved after we assign the neurons to the different samples. We want the neurons to remain close to each other, or the weights to remain close to each other if they are if they belong to neurons that are close to each other, right? So if this is W1, I want W2 and W3 to have similar weights because these two are close to my W1 weights. Okay, so for that I need to incorporate a neighborhood function, and the neighborhood function looks like this. So I denote it by phi of I comma j. So this is basically telling us whether I is a neighbor of j or it's not. So one common neighborhood function is the following. So we have 1 when the distance between neuron I and neuron j is smaller than a certain value, maybe r, and 0 if this distance is larger than a certain value, r. Okay, so that, for instance, for my grid here, for this grid, will mean that if the r was equal to 1, then this will mean that the neighborhood of this neuron is this neuron and this neuron here. And the neighborhood of this neuron here is this neuron and this neuron, and this other neuron as well. Okay, and then what we do with this neighborhood function is we modify the competitive learning algorithm. And now what we do, so we had in step 4, we were updating the weights only of the neuron whose distance to the input was the smallest. So the weights of the neurons which was the closest to that particular input. Now we not just update that, but we update all the weights of all the neurons that are in the neighborhood of that particular neuron. So say for instance that this neuron here gets selected and I'm applying this neighborhood function, then I'll update the weights of this neuron, of W, say W4, but I also update the weights of this neuron, the weights of this neuron, and the weights of this neuron. And this is sort of trying to maintain this topology, this structure in my neural network. So if we go back to the example of the movies, we could have a set of neurons. We could arrange our neuron like this. So now I have neuron 1, neuron 2, and neuron 3. And now I see that neuron 2 is close to 1 and 3, but neuron 1 is not as close to 3 than it is to 2. So this structure will be somehow preserved after I apply my learning algorithm. And what we will see in practice is that if the movies looked like this, so these were my movies, the different movies, I forgot, but sci-fi, maybe action, and drama, something like this. Then because this neuron here, if we apply this neighborhood function, will be updated both when neuron 3 is updated, but also when neuron 1 is updated. Then this neuron 2 will tend to be positioned after the learning happens, after we finish the learning process, will tend to be positioned in between the two, right? So the W2 is likely to be somewhere in the middle. And that's because it's basically updated, or it's basically influenced by practically all the samples, right? Because when, say, this was the position of W1, so when W1 gets selected, this neuron also gets updated, so it gets pushed to towards this part of the plane, and when W3 gets selected, then W2 also gets updated and is pushed in the other direction. But also when it is the closest to the inputs in this second cluster, then it's also updated. So this neighborhood function, together with the topology that we impose in our self-organizing map, is sort of what helps us to make sure that clusters that are close to each other encode related information. Okay, so this was all for today, and yeah, I hope it was useful for you, and yeah, I also hope to see you soon. Bye. And by the way, if you have any questions, you can always email them to me or also write comments to these YouTube videos.